Hey guys, this video tutorial, in your book, if you're following along, this video tutorial covers section 11-7. We are going to be talking about wave motion. Okay, so specifically, we're going to start investigating what are known as mechanical waves. Okay, now, mechanical waves are, computer. Mechanical waves describe what we typically see in the Newtonian mechanics type world. So these are waves that you'd see if you dropped a stone in water. The waves that you make with a slinky. You can shake a rope, stuff like that. So what's crucial to recognize is that water waves move with considerable velocity. Okay, so these waves move quickly, but it's important to realize that the actual particles of water do not have the same velocity as that of the wave. Okay, that's kind of tricky to wrap our head around, so think about it like this. I am right here on my boat, okay, and I'm just sitting on the wave. If you think about it, you say you bob along the wave. So you don't really move laterally with the wave. You bob up and down about an equilibrium point. Okay? So if we think about it, we can visualize it utilizing this PhET simulation here. So I've got a wrench here, and it's holding this string, and watch the green bead, okay? Now, if we think about it as the particles having the same velocity as the wave, then this bead should move further than where it is right now. But if you watch, it doesn't. It comes, well, if it catches up, it comes right back to where it started. It should land right back on the mouse, and yep, it sure does. So, the particles in the wave have a velocity that is up and down. But if we think about the wave as the crest, it has a different velocity, okay? It has a velocity that moves forward. So, remember, particles in a wave move up and down, okay? The wave itself actually moves forward. So, waves can cover a large distance, but their medium does not, okay? And, excuse me, I'm very important. And so, what those waves are moving, since they're not moving the particles, what they're moving is energy, okay? So the particles are just moving up and down, but what is moving forward is energy, okay? And so, how is a wave formed, okay? So, where do waves come from? Well, let's go back to our PhET diagram here, and let's change this to a pulse. Okay. Now, a pulse, let's write that out. A wave pulse is a single wave bump. Okay? So this is just a single wave bump. Okay. So let's look at our demo here. So, and did I start this? Yes, I did. Dang it. Okay, so what I'm going to do, this is going to, I don't want this. This is going to bob up and down real quick, and I'm going to change my end over here. Instead of fixed end, I'm going to make it no end. Okay, so I've got, you guys can't see it, but I've got a little window over there. So, pulse, phew, and it's gone. Okay, a single wave bump. So let's pulse, and then let's pause that. So what happened is I pulled up, and so here let's reset that and pulse and then stop. So I pulled up on the rope, and those particles felt that pulling up. And so as I move up, those particles move up with it because of the cohesive forces. Okay, so I pull up, the particles next to me move up. Now, I move it back down, and those forces feel that force moving down, and so they move down. So that's what creates that little bump, or a wave pulse. Woo. This is very fun if you guys go to PhET and you go to the wave simulator. So, one pull up, and then if we draw this out like this, these particles are feeling the pull up. These particles are feeling the pull down, okay, as are these particles. And so that pull down force gets transferred to the adjacent pieces of rope, creating that bump. Okay, so that is a pulse. Now, the other type of wave is known as a periodic wave or an oscillate wave. Okay, so if we come back here and we change this to oscillate, ooh, yay, we get a nice simple harmonic motion pattern here. So this is the reason why you the periodic or oscillating wave is why you can hear a tuning fork, why you can, or what you see when you drop a stone in water, or even why you can see objects. What we'll find out later is that electrons are vibrating, creating this light pattern, and vibrating electrons create light. So it goes down to the fact that everything that you see vibrates. So some useful definitions here. Let's pause this. Okay. So we know that this distance right here is called the amplitude. Okay, the distance from the equilibrium point is the amplitude. Now, a couple new definitions. We've got a crest, which is the top of the wave motion, and then we've got the trough, which is the lower end of the wave motion. Okay? So, let's come back here and let's draw a simple wave here. So, it's not a very good wave, but you get the idea. And here is my equilibrium point. So, I've got my amplitude, I've got a crest, and I've got my trough. Now, another definition that will be useful to us is wavelength. This is wavelength. Now, all this is, oh boy, wavelength. Now, all this is a distance from one crest to another crest, or one trough to another trough. Those are the easiest points to measure. Or really any point to its corresponding point. Okay? But the easiest way to measure it is from crest to crest or trough to trough. So this distance right here is known as wavelength. Now, frequency, when it comes to waves, frequency is the number of crests that pass a point per unit time. Okay? So crests over time. So the number of crests that pass a certain point over time. Now, we know that the period is given to us as 1 over my frequency. And let's look into wave velocity. Wave velocity. So, wave velocity, I'm going to make the v a little different. It's just v, but I'm going to make the v a little different to denote it from kinematic velocity. So wave velocity, if we think about distance over time, well, wavelength is just crest to crest, and then frequency is crest per time. So what I can do is multiply wavelength times my frequency, and that gives me my distance over time. So that is wave velocity. Okay? Now, another definition for velocity when it comes to waves, depending on what medium you're working with, is the square root of my tension force divided by my mass over my length. Okay? So, two definitions for wave velocity. All right? So now, let's look at an example of this. And let's go to, in your book, it is example, I think it's 11-11. It's on page 302. So it says a wave whose wavelength is 0.3 meters. So let's call this an example. So our example problem, this is 11-11. Okay. So it says our wavelength is 0.3 meters. And it's traveling down a 300 meter long wire, okay? So my total distance here is 300 meters. And the wire has a total mass of 15 kilograms. Okay. If the wire is under a tension force of 1,000 newtons, so my tension force is 1,000 newtons, they want to know what are the speed and frequency of the wave. So they want to know the wave velocity, and they also want to know the frequency. So since what they give us, 300 is our length, the variables that they give us coincide with this definition of wave velocity. So what we would use is the square root of 1,000 divided by my mass over my length. My mass is 15 and my length is 300. So plugging that in, I get a wave velocity of 140 meters per second. Now, frequency, look up here, frequency is, if I solve for frequency, it's velocity divided by wavelength. Well, they give me the wavelength, and I just solve for velocity. So my frequency would just be that over that, which gives you a number of 470 hertz. Okay? So, I ran out of pad over there, 470 hertz. So that's a brief example of just utilizing these definitions for wave velocity. So tonight in your book, I think you're supposed to do problems. Where are they? Pretty sure they're on Edmodo. Yeah, they're located on Edmodo, so get to that, and don't forget to read section 11-8. That is covering the different types of waves, transverse and longitudinal. Thanks for watching.